Hi, everybody. Welcome to the Virtual Foundries webinar, FFF Metal in the Classroom. We are delighted to have you as a part of today's event. It's Tuesday, January 18th, 2024. The time is 11:02 a.m. and the temperature is a nice warm 81 degrees Fahrenheit. That's 27 degrees for all you Celsius users. Now, there's a lot of talk about the heat this week, even though it really isn't all that warm. It's just a lot warmer than it has been. So kind of enjoying some real summertime temperatures here in southern Wisconsin. I'm Tricia Cease, president of the Virtual Foundry, and I'll be walking you through the webinar today. Now, if you're interested in networking with others using FFF metal in an educational setting, we have a couple of options for you. One way to connect with others is through the Virtual Foundry's Discord server. You'll see a link to the Discord server in the description of this video, or send an email to info@thevirtualfoundry.com with the phrase education networking included, and we will connect you with others who are interested. Now, moving on to the agenda and what we'll be covering. First, we're going to cover the basics. How does FFF metal work, and what is the general process for it? Next, we'll get into the good stuff about how FFF metal is impacting classrooms today and how you can get started with FFF metal in your own educational setting. We're going to talk about safety and other things that you need to consider as you work on setting up your own lab. And then we'll give you some educational resources. Again, we'll have some time for Q&A, and then we'll end with a summary. So let's get going with the basics of FFF metal. FFF stands for fused filament fabrication, and it's the most common style of 3D printing. It's sometimes referred to as FDM for fused deposition modeling. There's also bound metal extrusion, as we're getting into the metal version of this, and people come up with new acronyms all the time, but FFF is the most common. With FFF metal, you're using common equipment that you may already have to produce pure metal, glass, or ceramic objects. Now, all of the Virtual Foundry's filament 3D printing materials are made in generally the same way. So that is, we start with regular 3D printing PLA plastic, and we load it up with as much metal, glass, or ceramic as we can get into it. The PLA then becomes the binder holding these powders together. Because the powders are held together by PLA, they print just like PLA. Now, the resulting print has that same ratio of plastic to metal in it. And if you want your print to be pure metal, then you'll go through a debinding and sintering step. The debind step happens at 480 C or 900 degrees Fahrenheit. And that's the step that removes that plastic binder from your print. After that, a new heat cycle begins. And this is the sintering cycle that fuses the edges of those metal particles together. The sintering temperature is material dependent, and I'll show you where to find those temperatures on a future slide. Most stock filament materials from the Virtual Foundry complete the debind and sinter process in a standard kiln using open atmosphere, meaning no gas or vacuum is required. The two exceptions to this are aluminum and titanium, which do require specialized environments. So those two cannot be debound and sintered in a standard tabletop pottery type kiln. And once your part is sintered, you can do anything to that part that you would do to a piece of metal, glass, or ceramic normally. So we're talking about welding, brazing, machining, any of those processes. The final parts are microscopically porous, which is a property of powder sintering, and that property is controllable in this process. So FFF metal allows you to make full metal parts on your regular FFF style 3D printer and your regular kiln. Now, as an aside, we can also make custom materials. So if you've been wishing you could 3D print some metal that isn't available in filament form today, or you don't see it in our store, reach out to us and we'll talk about a custom filament just for you. So what equipment do you need to do this process? Well, number one, you need a 3D printer. The printer could be an FFF or FDM style 3D printer, but what kind? Well, our filament materials work in a broad range of those FFF, FDM style 3D printers. There are some properties that make a printer better for these materials. The ideal printer will be direct drive rather than have a bowed-in system, with the shortest filament path in the extruder. Printers must also be able to use PLA filament without restrictions to brand, so they're open architecture. And watch out for proprietary nozzles, as the hardened steel or other wear-resistant nozzles may not be available by that particular brand. And some manufacturers don't even make 0.6 millimeter versions of their nozzles. We recommend using a 0.6 or larger millimeter hardened steel nozzle with our materials, and a dual gear feeder helps drive the filament. Additionally, as we are talking about build plate material, glass build plates are fine, but spring steel is the best. Anything else may work, but we recommend covering other surfaces with blue painter's tape, since filament actually welds itself to PEI and PC build plates. Now, I just gave you a lot of information, but don't worry. It's in the recording, and it's also in that linked page that you see right there. The virtualfoundry.com/trusted-printers. So check out that webpage. You'll see that list of properties that I just mentioned, as well as a list of brands that we've known to work well with our materials. You'll also see a few brands that have given people trouble over time and would be helpful to avoid if you want to pursue a printer specifically for these materials. Now, this is not an exhaustive list. There are many printer brands out there, and as long as your printer has at least most of the properties mentioned, it should work well. You'll also need those hardened steel nozzles, a filler warmer to ease the path from spool to printer, and of course, your actual filament material. The second piece of equipment that you'll need is a kiln, which has only two requirements. It needs to have a programmable controller, because the debind and sinter time and temperature profiles have ramped temperature changes, and it needs to be able to hold the sintering temperature of your material for several hours. It's best if the maximum temperature of the kiln has a 50-degree Fahrenheit difference between its listed maximum temperature and the working temperature that you'll be running. You'll find a list of sintering temperatures on our website products page, and that looks like this with a chart of temperatures. Now, your kiln does not need to be gas or vacuum capable, since the materials will debind and sinter in open atmosphere. You'll also need a crucible, sintering powders, and we recommend using a crucible cover. So those supplies come into play when you're going into the debind and sintering process. You'll use that crucible, which is that cup container in the center there. You'll put some refractory ballast powder in there, and we'll tell you which one to use. Then you'll bury your print in that refractory ballast material. Place that crucible in your kiln, run the debind time and temperature profile, let the furnace cool to room temperature. You'll come back the next day and prepare your crucible for the sintering process. And then you'll place your crucible back into that same kiln and run the sintering time and temperature profile. Now, all of these instructions are clearly spelled out on our website on the how-to page. So take a look at that. You'll see all the instructions there. Now, there is some off-gassing during the debind process, and we'll talk about that later in the session today. Now, if you take a look at the kits that appear at the top of our online shop, you'll see how all of these supplies can be bundled together, so you don't have to worry about making sure that you have each one. You can see them there in that kit. Now, some of the benefits of using this technology in the classroom: your students can engage with this process hands-on, so the equipment is accessible to most ages. Your students can operate it, they can touch it, they can mess with it. It's not wildly expensive, so it's really student-friendly. You can adjust the parameters at every step to study the results. And you can keep the process fully in-house. You're doing it all yourself. So that's true hands-on learning. The technology is also low cost. You're using the printer and kiln of your choice, and it's 1/10 the cost of the closed systems, meaning a set of printer, devine, station, and kiln that all come together. There aren't any gas or chemicals used in the process, so it's also safer. And it allows your students to understand emerging technologies. They're getting involved in designing for 3D printing. Also considering how the printing parameters affect the process downstream, and they're learning about powdered metallurgy, which is a quickly growing field as metal additive manufacturing grows in industry and beyond. FFF metal is currently being used in education environments today in a few different ways. It's a part of the options provided to students and sometimes the community through maker spaces, fab labs, prototype labs, manufacturing labs, design labs, and others. That photo there in the first column is Professor BG of Halmstad University in Sweden. They included FFF metal in their fab lab, and that photo is from a podcast recording we did with the team there. I'll link that recording to this video and in the description. Students can learn about design for additive manufacturing with that extra element of considering downstream effects. They're doing projects like setting up their own metal 3D printing system, recording the steps that go into it, and then presenting to others about how to do that. And they're studying FFF metal in a couple of ways. So academic research includes a study of the process itself, the results, how the results compare to other processes, and sometimes a deep dive on one particular aspect of the process, like how printing parameters affect sintering. Applied research is very exciting and includes sodium-ion batteries, heat transfer, electromagnetic actuators, ammonia generation, and a host of others. So you can see a list of published papers on our website, and we continue to add to that list as we discover papers that have been published. You'll find a link to that in the description of this video. Now, another benefit to this technology is the people behind it. We want to talk to your students. You won't be in the dark trying to figure it out on your own. We can talk you through your project and give you any advice along the way. One of the interesting things about this technology is that it's accessible. It's being used in classrooms. It's affordable, easy to get your hands on, and easy to work with.
Nooner.
But what's also interesting is this is used all the way up to the highest end of the technologies, including Air Force research. We are starting at a research project that will take this exact technology to the International Space Station. They already have a plastic 3D printer there, FFF 3D printer, and they already have kilns. So in order to print metal on the International Space Station, all you need to do is add filament. And as time passes, we'll find more and more interesting and unique projects that apply this technology. It's expanding very quickly. So we've got different ages and skill levels of students working with the process now, kids younger than high school. And in that case, you would select a level of involvement that's age appropriate. Obviously, little kiddos can help select shapes and then watch them come into being. Older kids can start learning how to print and learning about the kiln. And at the high school level, kids can learn design and to do the full process on their own. Now, if you need a starting point, we have curriculum project kits to help. The kits include some electronic files with instructions and models and enough filament material to make 25 of the designated shapes. You'll find these on our website and in our online shop. Higher education has been really involved with FFF metal, and at that stage, these young adults are self-directed. They're creating projects, they're researching results, and they're publishing papers, the papers that you've been hearing me talk about. We can also serve as guest lecturers or do presentations to your class about this technology, metal 3D printing in general, or any other topics that would be interesting for you students. And we love to work with these students and researchers. We have collaboration agreements with the University of Texas at El Paso, the University of Pécs in Hungary, and we're currently working on a project with the Ohio State University that seeks to understand the FFF metal process in space that we just talked about a minute ago. Now let's talk about those considerations that you need to keep in mind as you think about installing your own metal 3D printing system in your lab. So thinking about safety, now there are no toxic chemicals in the process, so that's really helpful. You will practice good industrial hygiene when handling the sintering powders. You're going to be working with high heat, so you'll need some appropriate gloves like welding gloves. Your kiln should be installed at least 18 inches away from any other wall or structure or surface. And it should also be on a metal table as well, certainly not wood. We do supply SDS documents for everything that we sell, and those are at thevirtualfoundry.com/SDS. Now, on the topic of ventilation, I know that's an important one for many of you. So we'll walk through what's happening during the debind process and how you can help manage that. So if we use, for example, our bronze or copper filament, 85% of its mass is metal. So that means that the remaining 15% is PLA, polylactic acid. And the whole intent of the debind process is to remove that PLA binder from the part. So if, for example, you have a 100 gram part and 15% of it is PLA, you will have 15 grams worth of polylactic acid that needs to be vaporized. Now, inherently, polylactic acid is relatively safe, but it's still a chemical and it's still off-gassing. So the setup that's typically used, and you'll see this in nearly any art classroom, they'll have a vent over their ceramics kiln. The same setup is appropriate for the debinding process in FFF metal. We recommend that you ventilate during sintering also, but it's much less important. We'll do this just in open air in the office at the shop here, but during the debind process, it's very important that you ventilate or you're going to have aggravated people. The images that you see on the screen here are from Ventikiln. We don't have an affiliation with them, but you can learn more about venting and get some tips and ideas for that through a blog on our website. And we also have a video about it. Again, I'll link everything in the description of this video. Now, as far as material handling goes, all of that metal powder is encased in plastic. So you're not dealing with any loose metal powder at any point in the process. You're going to store your filament materials in standard indoor climate control, so really nothing special about that. They don't need to be stored especially dry. These materials are less hygroscopic than regular PLA, so a little bit more freedom in storage with these materials. And there aren't any toxic fumes released during printing. It's the same process as printing standard PLA. So at no point in the process are you melting metal. You are just 3D printing PLA, and those metal particles are going along for the ride. So ways that we can support you and educational resources that Virtual Foundry offers. We have about 3 different levels of that. We've got phone and email support, and we're always going to be here to answer your questions as you go through the process and get set up. Our YouTube channel is also a great resource for questions that you might have, seeing the process in action, and learning more about different aspects of it. We do offer a 4-hour training program that's going to be 4 60-minute sessions. We'll conduct those sessions at your schedule, and it's going to cover installation to finishing. So getting your system set up all the way through finishing your final parts. And then finally, we have the FFF Metal 3D printing course. That's 7 Zoom sessions over 14 weeks. It's 9 hours of instruction altogether that does happen at specified times on a schedule. For that course, we send you a kit of materials that you use to work through the process as the course goes. And then at the end, you'll receive a completion certificate, so you become the expert in FFF metal. Now, we can license either of these trainings for you so that you can deliver that to your students, to your colleagues. We can train your students directly, or we can teach you to teach your students. So we're happy to work out any kind of program that works best for you. So these are the 2 things that we have right now, the 4-hour training and the course. And the 2 things that we have set and ready. And again, we're happy to work with you to make a program that's going to work for you as well. We can certainly make a custom option for you as you need. So if you're looking to get started with FFF metal in your own educational environment, we have a couple of steps for you. Number one, you're going to get your equipment. You'll need a 3D printer, and you can use the virtualfoundry.com/trusted-printers for help if you don't already have a 3D printer, or if you want to see if your brand is on the list of brands that we have known to work well, or even if it's on the list of brands that we have known to give people some trouble. Take a look at that list. Some people want to have a 3D printer that's dedicated to these materials. That's not necessary since they're printing just like PLA. You can use the printers that you're already using to print PLA. So you don't need a special dedicated 3D printer. If you want to have one, that's great. The second piece of equipment that you need is a kiln. It should have a programmable controller, and it should be able to work at the required temperatures for several hours. We can help you with a kiln if you want to go through us. That's great. You're welcome to source a kiln from any place that you like. Now, just to get your feet wet and test the material out a little bit, you could try a filament sample. These are about 100 grams of filament material, and those are available in our online shop. You can get a filament evaluation kit, which is a mini version of all the supplies that you need to do the print, debind, and sinter process. It includes a green printed part and a sintered part, so you can see what those look like as well. And then a little bit more robust than that is the full print and sinter kit, which is that photo. And that's going to include a full-size version of everything that you need to do the print, debind, and sinter process. And then finally, certainly reach out to us for a quote. We can help you put together the perfect package for your lab or classroom. It's important to note that the kilns do have a 6 to 8 week lead time. So sometimes if you're working out your funding timing, that's an important consideration. We can also deliver kiln manuals to your safety department ahead of time, so they can look through that and make sure that they are preparing correctly to install the kiln. Taking a look at some of the questions that have come through in the chat throughout the webinar, what is the average cost of the course? Well, the course is around $2,000, so it has tiered pricing based on when you register, starting at something like $1,950 and going up to $2,150. So consider that it's around $2,000. That 4-hour training course that I mentioned is $1,500, and those are all US dollars. Next, powders are needed for sintering and debinding that requires people to be careful. Yes, you will practice good industrial hygiene when working with these powders. The jars are labeled that there's loose powder inside, so you'll be prepared when you open the package of those powders for what you're going to find inside. But yes, good industrial hygiene, standard safety practices for those materials are important. We have SDS documents for all of that so that you know what you're working with. We do want to clarify that people just starting out for your first time, we strongly encourage you to start with either copper or bronze. There are baseline materials. They were the first that we brought to market, and it's what we have the most history with. It's what we find people find the easiest to work with. So it's a good place to step in. Now, are the powders purchased separately from the metal and ceramic filaments, or are they included in the purchase? Well, the powders are a separate item, but if you look for those print and sinter kits in our shop, they will all come together in that kit for you, or you can buy them separately. The sintering powders can be reused, and you can look for a blog on our website about that, or a video on our YouTube channel that explains about how to reuse those powders. What inert gas is recommended instead of sintering powder? So during the sintering process, oxygen needs to be prevented from reaching your part. The Virtual Foundry does this in an open atmosphere by using sintering carbon on top of the crucible. The sintering carbon reacts with the oxygen and prevents it from reaching your part. Now, if you want to use gas or vacuum to prevent oxygen, you can certainly do that if you're familiar with that process. So the question is, what inert gas is recommended if you're going to go that route instead of using the sintering carbon? And we don't directly support this technique just because it's highly variable. And anyone who would do this likely has a fair amount of expertise on the topic to begin with. But the gas that you would want to use is whatever is appropriate for the metal that you're working with. So for example, if you're in TIG welding, stainless steel, for example, you would use a mix of argon and CO2. So that's likely a pretty good catch-all gas for the materials, but a little bit of research needs to be done on what gas is appropriate for sintering and which particular metal they do vary. Can you explain why 0.6 millimeter is the minimum nozzle size? The powder is so small, it seems like you could print with smaller nozzles without blockage from bridged powder particles. And you can, and what happens is it's analogous to a traffic jam. You know, all the cars will fit down the highway, just not all at the same time. And it doesn't mean that you can't print with a smaller nozzle. The numbers that we provide are the numbers that are the most likely to get you success and as little frustration as possible. So we know that if we tell you to start with a 0.6 millimeter nozzle, you'll succeed. At 0.4, you won't always fail, but you won't always succeed. So your success rate may go down a little bit as the nozzle size becomes smaller. With our tungsten material, we've printed parts all the way down to 0.3 millimeters, so it can be quite small. The reason we recommend it is just ease of use, not necessarily success or failure. When we're talking about a closed chamber, do we mean the printer? Does it require a closed chamber like ABS or high-end plastics? A closed chamber 3D printer is not necessary. We do see the Bamboo Labs, it happens to have a closed chamber, and we use the Ultimaker S5, which also happens to have a closed chamber, but that isn't what's important about it. Most of the printers that we work with and the ones that we run in-house here are just open frame Creality type printers. So a closed heated chamber is absolutely not a requirement for the printing process. If you can print PLA, you will succeed printing these metal filaments. They work the same. I'm a little confused about the powders. It's filament-based printing. What's up with those powders? So if you look at it, if you look at the filament under a microscope, it's just millions of little metal particles included together with a little bit of polylactic acid, that thermal polymer. And where the powders come in is really in that debinding and sintering process when we're talking about powders throughout the FFF metal process. So you're burying your printed part in a refractory ballast, is what we call them as a group, or we call them sintering powders as a group. But you're burying your print in a refractory ballast material. For copper and bronze, it's Al2O3 or aluminum oxide. And that material then provides part shape support as you go through the debinding process. Then when you're getting ready for the sintering process, you'll pack your print in magnesium silicate, which provides part shape support, but also easily moves out of the way as your part shrinks on itself during the sintering process. And then during sintering, you're also applying sintering carbon to the top. So that's where the powders come in. It's in that debind and sintering process, and they're used to support your part shape and mitigate oxygen. But all of the metal powders are encased in plastic, and the printing process is just printing PLA. Now, the next question, will we have finishing instructions? And from the questioner's experience, finishing is a little involved to have beautiful artifacts as like they see in the photos on our website. We do have a finishing page on our website that gives some instructions. And we have a podcast that talks about finishing your sintered parts, or cleaning your sintered parts, I think is the terminology that we use in that podcast if you're looking for that on the YouTube channel. But how you finish your part is going to depend on what you want your part to look like. The pieces that we show on our website, probably 95% of them, we just put them in a rock tumbler with stainless steel media and some tumbling compound and tumble them for half an hour to an hour. Now, there are very specific instructions on the website, so that's the easiest, the least labor-intensive method of finishing your part and getting to something that looks nice, like a piece of metal. Going beyond that, you can use any metal finishing technique that a jeweler may use. So you can hand polish, you can file it down, you can get it down to a mirror surface if that's what you're looking for. But yes, that is labor intensive, as it is with any piece of metal. And these properties aren't unique to the virtual foundries process. You'll find that everything that I just said is also absolutely true for even the most expensive multi-million-dollar printers. You do not get a shiny finished part out of a $1 million laser powder bed printer either. Now, is it possible to use multiple types of filament in one print? Like, could you print supports using PLA on the part with metal? The answer is absolutely yes. And for support material, if you only have one print head, you're just going to wind up using more of the metal filament material. But any of the support materials that work with PLA are compatible with our filament. So you can use the water soluble or even solvent dissolvable, whatever you want. Anything that works with PLA that you can buy off any of the retail sites will also work with our material, or just use inexpensive PLA as your support material. So you can use those PVA water soluble supports, and soaking your part in water is totally fine. Can you use a sandblasting chamber? Because some additive manufacturing labs may already have these for removing powder from metal or SLS prints. Yes, and in fact, these work really well. We don't talk about it much because not many people have them, but for those that do, it's an excellent solution. Blasting and pellet blasting with ceramic media or steel shot media or any of those kinds of things, they really provide a nice surface, and they have the effect of work hardening the part. So it's like tapping it with a million tiny hammers when you sandblast it. So it gives it not only a nice looking finish, but it gives you a slightly harder finish that will take a higher shine. Okay, now we'll go on to the summary and key takeaways. The FFF metal process is safe. It's hands-on for your students. It's flexible, it's variable, it's low cost. It allows your students to engage with emerging technologies. It greatly expands your research options. Your students can learn about design for additive manufacturing with metal, and the Virtual Foundry takes a collaborative approach. We can teach you to teach others. Finally, here you'll see a list of resources and places you can go for information and more detail about the process, about the Virtual Foundry, where to engage with other people who are working with FFF metal. The best place is in the Discord server, that top item there, and we look forward to seeing you in there. Well, thank you for joining us today. We are certainly available for any questions following the sessions or any questions anytime. So write to us, reach out, info@thevirtualfoundry.com. We'd be happy to help you set up your own metal 3D printing lab and get you set up to teach your students how to use this really exciting technology that will really enhance your and their research. Until next time, happy printing, everybody.